In this video, we look at some other criteria and irreversibility in project evaluation. The other criteria that are used for evaluating projects include cost-effectiveness analysis, multiple criteria decision-making, which is my preference, life cycle assessment, LCA, and cumulative effects analysis. Cost-effective analysis is used when the objective cannot be valued in monetary terms, or stakeholders are reluctant to measure things as health impacts and human lives saved or human lives bettered in monetary terms. Cost effectiveness analysis identifies least cost strategies for achieving a non-economic objective. Therefore, it's used in health, education, environmental, and defense programs and policies because programs or policy benefits are generally not easily or accurately measured in monetary terms. The information summarized by cost effectiveness analysis can be summarized in this cost effectiveness ratio, which is that CO minus CX divided by EO minus EK, where subscript 0 and K describe intervention under consideration and the alternative to which it is compared. So CO and CK, not X, CK, are associated present values of costs, and E0 and EK are the respective health outcomes measured in some fashion. All right, so we've got a cost of one particular intervention minus that of another type of intervention. Maybe that intervention is to do nothing, divided by a measure of the effectiveness of the intervention minus the effectiveness of the intervention to do nothing. So these are compared using this CE ratio. Multiple criteria decision making focuses on trade-offs between different objectives or accounts. So the Water Resources Council in the USA employed an accounts analysis. All right, they had basically 4 accounts: national development, which was their economic efficiency account; regional development, which included local employment, for example; the environment; and other social effects, these kind of intangibles, if you like. So national development was the one that we use in social cost benefit analysis. Regional effects also could be some component of economic efficiency. They could be measured. And environment could be measured using non-market valuation techniques, for example. Other social effects, that was much more difficult. Now, the explicit effects on other accounts need to be clearly identified. So opportunity costs were to be expressed in monetary, in other words, foregone economic efficiency, and in non-monetary terms. Trade-offs had to be clearly identified, so jobs versus carbon uptake in an energy project, for example, but it was more important to look at jobs versus economic efficiency and then a carbon uptake versus economic efficiency. So the Water Resources Council required trade-offs relative to economic efficiency, so not jobs versus something else, environment, for example, or jobs versus how much carbon uptake there was. All right, both of those objectives had to be, or both of those accounts had to be taken compared to each other through the monetary values. The techniques available to make explicit trade-offs in decision-making included such things as goal programming, compromise programming, and the one I liked the best was fuzzy compromise programming because it gave you a clear idea of how much you were giving up when you managed to get parts of each, or how many parts of each of the accounts or objectives that were attained. Life cycle analysis evaluates effects of a product, the effects that a product has on the environment over its entire life. It's a cradle to grave analysis. As a result, it's a continuous process with companies able to begin a life cycle analysis at any point in the product cycle. It can be used to meet ISO 14000 series environmental standards, and it might be useful in identifying the external costs that are often ignored in standard social cost benefit analysis. For example, when we're talking about wind turbines and the costs and benefits of employing renewable electricity, we could look at costs associated with the mining of lithium and cobalt and rare earth minerals, and which are needed for batteries. And we could look at the costs of disposing batteries, and those are the kind of things that we ignore when we determine whether or not wind turbines are worth building and allowing that electricity to enter into the grid. Finally, there's cumulative effects analysis. The problem of cumulative effects is that it occurs in an externality context and it only informs cost-benefit analysis. Examples include primarily, and this is a really good example, where a municipality has a waste treatment plant, but it's limited capacity, and at some point in the future, the next home that's going to be linked to the waste management plant, waste treatment plant, requires, you just can't add another home because you've hit the limit of your capacity. So efficient pricing, of course, requires that residents pay the marginal cost of waste treatment, but as more residents are connected to the system, capacity is eventually exceeded. And the dilemma for efficient pricing is that efficiency requires that the last person or firm that's added to the system, the marginal user, would need to pay the entire cost of a new capacity. The inframarginal users are just as responsible for overloading the system. Now, inframarginal users are those that were charged the marginal cost because it's like putting a bridge up. Once a bridge is up, the marginal cost of getting anyone across is zero. But once you hit capacity and once you hit congestion, the cost goes up. The inframarginal users are those who use the bridge without causing congestion. But as soon as congestion is reached, then the marginal user, the last car, which results in the congestion, then increases that marginal cost and is no longer an inframarginal user. So the inframarginal users are just as responsible for overloading the system, just like the inframarginal car users are with the bridge. So to fund the additional capacity, you need to use a system development fee, for example, so that each new user, when they become connected to the system, they have to pay this fee. And eventually, you'll have enough funding to replace the plant once its capacity is exceeded. Cumulative effects analysis seeks to measure points where environmental damages become sufficiently great that investments in conservation and environmental improvements are warranted. And then finally, we come to irreversibility and extreme events. There are three means to address extreme events and possible irreversibility. First, to determine the cost of an extreme event or irreversibility and figure out its probability of occurrence. Then we include the expected cost in the cost-benefit analysis. Some problems are that we don't know what the probabilities are. It's a case of risk where we can estimate the probabilities versus uncertainty where we are totally unable to figure out what the probabilities might be. And there's the question of fat tails. In other words, where an event which is considered rare is actually given a higher probability than what one might suspect. For example, a nuclear power plant, the probability that an accident occurs is extremely low, but those who worry about that consider that probability to be very high, which means they have a fat tail in their distribution for that kind of event happening. The most commonly applied criterion is the precautionary principle. The precautionary principle is defined as follows. When an activity raises threats of harm to human health or the environment, precautionary measures should be taken even if some cause and effect relationships are not fully established scientifically. The European Union prevents research, development, and adoption of genetically modified organisms in its agriculture under the Cartagena Protocol on Biosafety from 2000, and that was put in place under the 1992 UN Convention on Biodiversity. The problem is that the precautionary principle is logically inconsistent and, if taken seriously, can be paralyzing. Now, economists they sometimes think about what's known as a safe minimum standard of conservation, which was introduced by Subrasi Wantrup, an agricultural economist at UC Berkeley. The safe minimum standard says, choose in favor of the strategy that provides the greatest flexibility and the smallest potential loss, and this is the key, unless the social cost of doing so is unacceptably large. What is unacceptably large? So it works like this. Suppose you have a matrix of losses. If you have a development strategy and the state of nature number 1 comes out, there's no loss. If the state of nature 2 comes out, then the development results in a loss, and the maximum loss is y. If you choose the safe strategy and the state of nature number 1 comes out, you lose the cost of that strategy. All right? There's no redemption, so to speak. In other words, the strategy of development was better. However, if number 2 shows up, then the benefit or the loss is x minus y. All right, the minus y because you've avoided this cost of development. So both x and y are positive here, of course, and the minimum, or if we want to minimize the maximum loss, then if y is greater than x, you choose s. So if we go back, if y is greater than x, then you choose the safety. And if y is less than x, you choose development. All right? Now, that's what the mini-max solution would be to that problem. But what if x is only slightly bigger? If x is only slightly bigger, then you should probably choose s. What about flexibility? Choosing s safety might not preclude development in the future, but choosing development might preclude s in the future. So what about probabilities? Do we know what the probabilities are? Perhaps not. What about the certainty of payoffs, of loss estimates? Do we know these with certainty? The SMS rule, of course, is adopt S, the safety, unless social costs of doing so are unacceptably large. The problems are that both the safe minimum standard and the precautionary principle abandon cost-benefit analysis as a decision rule. Could cost-benefit analysis be constrained by either? And when are costs intolerably high?